we're going to isolate the small area increment we get from the jth x interval and the ith x interval and the jth y interval. And we're going to consider what it contributes to the moment of inertia. We'll have a sample point. And we're going to label that sample point xi star yj star. To calculate the moment of inertia of this small interval, we have to determine first its mass, and that's going to be easy. We're going to multiply our delta x by our delta y to get the area, and we're going to multiply that by our density, which is always 1/2 gram per square centimeter. So that density is not going to depend in this case on our position on the domino. To get the moment of inertia, we've also got to determine or represent our distance from the axis of rotation. We call that distance r, and that distance is going to, not getting a very good straight line there. We're going to call this distance r. Now again, assuming that this is the origin, what is the distance r from the origin to the sample point within our interval? Because remember, everything we calculate for the interval is going to be calculated at the sample point. It should be clear that, let's move over here a little bit, that r is going to be the square root of xi star squared plus yj star squared. And just to be specific, we'll call that rij. It follows that our delta m ij, our contribution of this ij area increment to the mass of the domino, is going to be 1.2, and that's 1.2 grams per square centimeter, times delta x delta y. Delta x and delta y being the dimensions of this increment, and that our contribution to the moment of inertia from the ij interval is delta m ij times rij squared. Our contribution to the moment of inertia then from the ith interval of our x partition, and I'm kind of abusing notation here, I'm going to call that delta I sub I. That's going to be the sum from j equals 1 to m of all the area increments, the sum of the moments of inertia from all the area increments in this strip. And remember that that y partition, or y partition y from y naught to y sub m sub intervals. So that this expression is going to contain all of the area increments in the ith strip. So that's going to be what? It's going to be the sum over the j's of our delta m ij rij squared. Our total moment of inertia then is the sum from I equals 1 to n of the moments of inertia of all these strips. and that's going to be the sum from I equals 1 to n of the sum from j equals 1 to m of our delta m ij rij squared, which, substituting delta mij equals 1.2 delta x delta y and rij square root of xi squared plus yj star squared, becomes a sum from I equals 1 to n of the sum from j equals 1 to m of 1.2 square root of xi star squared plus yj star squared squared times delta x delta y. Writing that down once more and changing orders just slightly for convenience. Okay, we're going to go ahead and square the expression for r. So we're going to have 1.2 times xi star squared plus yj star squared, and then that's going to be times delta x delta y. Since I'm summing with respect to y first, I'm going to change that to delta y delta x. And just to be careful, I've gone off camera for a second and changed all these equalities to approximately equal, and we'll change this one similarly. And now, without a lot of further discussion, I'm just going to say that this approaches as delta x approaches 0, delta y approaches 0, so that n approaches infinity, m approaches infinity. This approaches the integral of an integral of 1.2 x squared plus y squared dy dx. The limits on the integral are determined very easily by the limits on our partition. Now, our x partition had limits 8 and 13, so that's the integral from 8 to 13 with respect to x of the integral. Our y partition went from negative 1.25 to 1.25. Now, in the preceding example, the y partition had limits that depended on some function f of x, but that's not the case here. This is a rectangle. The y limits are what they are, and they don't depend on the x position. And that simplifies life a little bit. All we have to do is write down the limits then on the y partition, and they apply then to the y integral. Those limits determine the limits on the y integral, and we get quite a simple integral here. And let's go ahead and finish this integral off. Okay, well, we're going to integrate the inner integral, so we'll leave the outer integral for the moment untouched. Our inner integral, and let me do one other thing. Let me go ahead and factor this 1.2 all the way out, because it's a constant. It's going to factor out of this integral, then it's going to factor out of this integral. And now we've just got to integrate x squared plus y squared with respect to y. Our antiderivative is x squared y plus y cubed over 3. And that's going to be evaluated between negative 1.25 and 1.25. Now, x squared y is going to give us x squared times 1.25, and I'm going to write this as 5/4 And then we're going to have 5/4 cubed over 3 minus the quantity x squared times negative 5/4 plus negative 5/4 cubed over 3. And let's kind of circle this as a side calculation. And then say that our integral is 1.2 times the integral from 8 to 13 of, okay, we got x squared times 5/4 minus x squared times negative 5/4. That's 2x squared times 5/4, which is 5/2 x squared. 5/4 cubed is 125/64. 3 times 64 is 192, so we have 125 over 92 here, and minus the minus is going to give us another 125 over 192, and that's going to end up being just a pure number, and that number is going to be 125 over half of 92, which is 125 over 96, if I do my arithmetic correctly, and as usual you need to remain skeptical about that. Now, in doing this inner integral, all our y dependence is going away. We end up with a very simple expression that we easily evaluate, that we easily integrate with respect to x. Finding an antiderivative, which is going to be what? 5/6 x cubed plus 125 over 96x. We then plug in x equals 8, x equals 13, find the change in our antiderivative, multiply that by 1.2. I'm not going to bother doing that arithmetic on screen. Evaluating that integral, we're going to end up with something around 1700. I think around 1690 something. Now, our x and y units were grams, were centimeters, and our mass units are grams. So this turns out to be 1700 gram centimeters squared. We can compare this result with what we would get if we assumed the entire domino was, the mass of the entire domino was concentrated at its center. Its center is halfway between 8 and 13 centimeters, 10.5 centimeters from the axis of rotation. Its mass, recall, was 15 grams. And if we multiply 15 grams by the square of 10.5 centimeters, (15 grams) times 10.5 centimeters squared. 10.5 squared is about 110, times 15 is going to give us about 1650. Now this is a little bit less than this, and that turns out to be as it should be. Remember, we're multiplying by squared distance from the origin. On this half, the squared distance averages more than it does on this half, and it goes up non-linearly. The further we move to the right, the more our influence of r squared increases with each interval, so that the actual moment of inertia is going to be somewhat higher than the moment you would get if you considered this thing to be all concentrated at its center.